so the ruler's telling me, so the tool tells me about the accuracy. So let's say I had two different tools. In the first lab you do, you're going to have different tools, and you're going to have to figure out how to report your answers. So I'm going to measure the density of something. Okay, good. So sometimes if you forget that formula, you remember right away. It's how many particles are in a given volume. Okay, so let's say I'm measuring my mass with a tool to the nearest tenth and my volume with a tool that's accurate to the hundredth. Does one of those tools limit the reliability of my answer? So I can't use the most accurate tool to report my answer, right? I can only use my least accurate tool, right? So that's why we use, when we do the calculations, we use the one with the least number of significant digits in the answer, or in the tool. Okay.
I have a question.
Yep.
Why would there only be two significant figures in 240?
Because there's no decimal, and you'll know in 5 seconds. Here, we'll just go up here. So these three paragraphs say exactly what we just established. All right, so here's the rules. And so if I were a guy or gal and didn't memorize the rule, I'd write them on my index card for the test down the road. Or when you're doing your homework, it's easy because then it's right there in front of you. And there's two ways to do this. I think this is, we'll see a better way in a second. But anyway, rule 1, and those were in the blue box basically, where it said tips. They really were rules. All non-zero digits are significant. So any digit that is not 0 is significant. So right here where it says 325 milliliters, all three of those digits are significant because none of them are a 0, right? Okay. And here again, this same deal, 1.325. There's 4 non-zeros, so there's 4 significant figures there. Okay, and then for zeros, then B, it says zeros may or may not be significant. To determine if a 0 is significant, use the following rules. Zeros appearing between non-zeros are significant. So this 0 is between two non-zeros, right? So that's 3 significant figures. These two zeros are between two non-zeros. So that's 5 significant figures. Zeros in front of non-zeros are not significant. So these zeros are in front of non-zeros. So they're not significant. So there's only 3 significant figures in this statement. So how many significant figures are in this statement? Right here. 0.0002. That's the only one, because all those other zeros are in front of it. So here's this. Zeros at the end of a number to the right of a decimal are significant. So that means these zeros are significant. So I have how many significant digits in this? Zeros at the end of a number to the right of a decimal are significant. So how many significant digits? 4. Now, says zeros between non-zeros and significant zeros are also significant, and that's so they're saying zeros between non-zeros, zeros between non-zero digits and significant digits are also significant. So here's my non-zeros and zeros, and these are significant, correct? They're to the right of a decimal. And it's saying zeros to the right of a number and after a decimal. And then the zeros in between of the significant zeros are also significant. That's a mouthful, right? So there's 6. So all of those zeros are significant because there's a decimal that makes these 2 zeros significant, which by definition makes the other 2. That's a bunch. Okay, and then here's the caveat though. Zeros at the end of a number, but the left of a decimal may or may not be significant, which is this situation we just talked about. May or may not be significant. If such a zero has been measured or is the first estimated digit, it is significant. On the other hand, if it hasn't been measured, but it's just a placeholder, not significant. So for this exercise, you're going to assume they're significant. So just assume they were measured, because that's the deal, is they may be and they may not be, those 2 in the middle there. Depends on whether you actually measured them. But it kind of makes sense, because if you are a scientist and you report this number, then you're telling the reader really that you measured those, right? If you put them down there at all, right? Which then means these matter too. If these matter, then these must matter too. And so here's another example. How many significant figures in 3,400? 2. No decimal. There's no decimal. And how about here? 4,000.4. Right, because there's a decimal there. Okay, and here's the other way that if it were me, I'd put this on my card instead of all those rules. Is this flow chart. So first it says look for non-zeros. They're all significant. Then it says look for zeros between non-zeros. They're significant too. Look for a decimal point. If there is a decimal point, look for the zeros at the end of the number. They're significant. If there's no decimal point, then you just add them up. So I like this version better than the list all the rules, because it's sort of the order you would do it in. All right, so let's look at these examples. 30040. So there's only 4, because this one is not bounded by non-zeros. There's no decimal. So it's a placeholder, right? So clearly this and this are not the same number. They're off by a power of 10, right? So it has to be there, but it's only telling me what power of 10 the number is, right? Okay, so how about 0.663? 3. That 0 is to the left of that decimal, and it's really not even a placeholder. It's just a convention that they put it there. So when you report your answers, you really don't even need it. Okay, how about 20.05? Easy, because right away, you don't even need to worry about the decimal, right? Because those are bounded by non-zeros, which makes them significant. So you don't even have to look for decimals. And 1,500 point. And how about that? 2. How about that? Right, because there's a decimal, right? There's all zeros over here. So these zeros are to the left of that non-zero. Not to the right of the non-zero. They're to the left of the non-zero. Okay, so if we go back to another density example, how many significant digits are in this number? 11.079. How many significant digits are in this number? So my answer can only have 3 significant digits in it. So I have to go with my least accurate one. So I got, my calculator spit out 0.872 blah, blah, blah. But this limits the number of digits I can report. So I have to get rid of all of these and round it to there. Here's a good one. 3 students measure volumes with 3 different devices. They report the following volumes: 164, 39.7, 18.16. If they pour it all into a single container, what's the total volume? So you're adding, right? What steps are needed? Add the volumes, V1, V2, and V3, and you get 221.86. Round the number to the same number of decimal places as the measurement with the fewest decimal places. So 164 had no decimal places, right? No decimals. So my calculator says this, but I can only say this. So I have to round this number up because I only have, my least number of decimal places is none. Does that make sense? So I'm not really so worried about significant digits there as I am keeping track of my decimal place. So the adding and subtracting rule is different from the multiplying and dividing rule. Okay. How many significant digits are in this number right here in A?
3.
And 3, 3. And there's the 3 in my answer. And this one? 2. Left of a non-zero. Not bounded by non-zeros. Left of a non-zero, not bounded by non-zeros. 4, 3. So my answer can, whoa, 1, 2, 4. Why is that? 4, 3. Yeah. This one, wait a minute. This one's significant, right? Because I measured it. Otherwise, I wouldn't have gotten this digit. Sorry, so that's significant. 4 and 3. But I'm adding, so I go with the addition rule, which is the least number of places past the decimal, which is how many? 3. So my answer will go 3 places past the decimal. So here I have 4 significant digits total. So I'm not using that other rule. I'm not using the multiplying and dividing rule. So watch that.
Wait, so why is it 0?
This one?
Yeah.
Because if it's there, then I measured it. Okay, but we can go back to the may or may not be too. We can go back to the may or may not be rule. And here is 2 significant digits, 2, 2, and here's 2, 2. So it does follow the rule, but it also follows the no decimal. So I can't count anything past that decimal place. So there's my 150.
Why does it have 3?
Why does it have 3 digits or?
Never mind, there's 2 because the 0 doesn't count.
Right. And in this case, I care more about, I can't count that thing past the decimal because these 2 things don't have decimals. Okay, so she's making an observation that shouldn't confuse scientific notation with significant digits, right? So all that 0 is telling me is about power of 10. It's not telling me anything about whether I measured it or not. So if I said this, I'm telling the reader I measured that. If I'm just saying this, I'm saying it's not 15. It's 150. It has nothing to do with whether I measured it accurately or not. Okay, so put this in your calculator. Ready? 253.05 plus 33.9 plus 28. What do you get, Justin?
You get 314.95.
Oops. $314.95. Okay, so I had, and you still have those numbers in front of you on your calculator. Is that going to be my answer?
No.
What's my answer going to be?
315.
Why is it going to be 315? So when I look at 28, do I have anything past the decimal?
No.
Nope. So neither can my answer.
So you just round up.
So I can only have as many digits as I have past a decimal. And I don't have a decimal at all in 28. So my answer can't have a decimal. So I have to round up. And when you do the problem set, you'll get like some ginormous number plus some other ginormous number, and you're going to have to round up like 30,000 digits. And that's okay, because you're still following the decimal place rule. Okay? Division. All right, 14.9. Yep, divided by 3.0. 14.9 divided by 3.0. What's my answer? Everybody get 5.5?
I got
4 point what?
4.966.
Okay, 4.966. Okay, so I have to round that to how many places past the decimal? Well, actually, but I'm going with the significant digit rule now because I'm not adding. So what's my least number of significant digits? 2. So my answer has to have 2.
So it'd be 5.0.
5.0.
Why wouldn't she just have 4.7?
Because it was 4.9 something something. But yeah. So if it was 4.6 something something something, it'd be 4.7. How about 13.75 times 10.1 times 0.91?
9.1.
0.91. No, 0.91. So 13.75 times 10.1 times 0.91. Answer. Okay, how many significant digits am I limited by? What's my least number of significant digits? 2. So what's my answer?
13.
close. That's that same thing you got stuck on, 130. So that 0 doesn't count, but it's telling us it's 130 and not 13. And there's a big difference, right? Yeah. It'll make sense here when we do scientific notation. Chelsea, it'll make perfect sense. Okay, one more of those. 6.975 times 30 times 21.5.
6.795,
Yep, 6.975. 975 times 30 times 21.5. Okay, but so how many significant digits are in the number 30? So my answer can only have one significant digit, so it has to be what, Ashley? So I have to throw all those other numbers away. So if you don't get why, go back to the ruler thing. So I can't say, so if I have 3 measurements, my least accurate one is here, which is an estimate, which is 0.4 or whatever, 0.4. Then I can't report if that's my least accurate number. So I can't, even though this one is 6.589, I'm limited by this least accurate measurement. So I can only put however many that least accurate one has. Okay, rounding rules and significant digit rules. Love them, embrace them, learn them.